Okay. So thanks for inviting me and giving me the opportunity to speak in the Nottingham seminar. So I will report on joint work with Anne-Sophie Kaloghiros, and this is about some examples of K-polystable Fano varieties which produce singular points in K-moduli. And this happens both on the stack and on the moduli space. So the plan of my talk is, at the beginning, I will try to talk briefly about Fano varieties and their moduli or deformations. Then I will talk briefly about good moduli spaces and K-moduli. And this is basically the work, the recent work done by many people. And then at the end, I will show two examples. In one case, this is a toric threefold with Gorenstein singularities, which has different smoothings. And so this is a singular variety which can be deformed to different smooth Fano threefolds. And for instance, in this example, it happens that the stack has 4 branches. So there are 4 components in the versal deformation space. But when you consider the K-moduli, so the K-moduli space, the good moduli space, then 2 of these components are identified. And so now the algebraic space there has 3 branches, not 4. And then the second example I want to talk about is an example where the K-moduli stack is a fat point modulo a group, and the K-moduli space is a fat point. Actually, it is the ring of dual numbers. And both examples are produced by using toric geometry. And toric geometry is very helpful because you can use the combinatorics to run completely all the computations, explicitly, basically. Okay. And another thing that I want to say is that whenever you have questions, please interrupt me. Okay, so I will work over C all the time, and I will consider Fano varieties, which are normal projective varieties X, such that the anti-canonical divisor is Q Cartier and ample. So when I say Fano, I don't say anything about the singularities. And now, if I fix n an integer, a positive integer, and v a positive rational number, I can construct which I denote in this way, m and v Fano, the stack of Fano varieties of dimension n and anti-canonical volume v. So this stack parameterizes exactly Fano varieties of dimension n and degree b. So this is a stack, and so this is a pseudo functor from the category of schemes to the category of groupoids. And so basically, for every T scheme, we consider the evaluation of this functor on T. This is the category of flat families from curly X to T, which are flat, proper, of finite presentation. And then we require that the fibers are Fano varieties of dimension n with volume V. And there is also another condition, which sometimes is called Collar condition, some other times is called the Q-Gorenstein or QG condition. And this is a condition about the fact that the canonical divisor, the anti-canonical divisor, behaves well in families. So it's a condition regarding basically the anti-canonical divisors of the fibers. So that the anti-canonical divisors of the fibers glue to a global divisor. And I will not talk about this condition, but maybe it's helpful if I say that this condition here is automatically satisfied if the fibers of the morphism are Gorenstein. So in the examples that I will show, the first example is Gorenstein, and the second one is not Gorenstein. And I will tell you briefly what we should do in that case. So you should consider the canonical cover, but I don't want to talk about this. And every time I write deformations of families, I will always assume that I'm considering Q Gorenstein families or families satisfying color conditions. Okay. The thing about this, so this is a stack, but this is pretty nasty because it's highly non-separated. And the reason is you can create families of smooth Fano threefolds, Fano varieties, they generate into something, but on the general fiber, you have an isotrivial family. And so this is a problem for the separatedness of moduli. Okay. Nonetheless, you can consider the local structure of this moduli, and this is given by the usual infinitesimal deformation theory. So for instance, if you pick X, a Fano variety of dimension n and anti-canonical volume V, then I denote it in this way with the curly bracket around X, the corresponding point in this moduli stack. And the local structure of this moduli stack at this point is controlled by the action of the automorphism group on the functor of infinitesimal deformations. So this is the usual usual theory of infinitesimal deformations. And what is this functor? So basically, you consider the category of fat points, the opposite categories, or equivalently, the category of local Artinian C algebras. And then you consider the functors which associate to every fat point the deformations of X over that point. So in other words, this is the restriction of M of this stack to this subcategory. So I'm considering not every schemes, but only zero-dimensional ones, local zero-dimensional ones. And so basically, I write again the definition. I have that I have families which are flat, proper, of finite type, and then here I require that the closed fiber is X because there is only one closed fiber, and then of course I require the color condition. And here I also use this notation for this these vertical bars to mean that I'm not considering the groupoids but the set. So this is the set of isomorphism plus. And the local structure of this moduli is given by basically the action of the morphism group of X on this functor. And this functor has hull, or equivalently a Kuranishi space, or a mini-versal deformation space, and this is the atlas for the stack, basically. And as usual, in infinitesimal deformation theory, I have T1x, which is defined as x1 of omega x ox, and this is the tangent space of this functor. So this is exactly def x evaluated on C T square. And then there is also T2x, which is defined as x2 omega x ox, which is an obstruction space for the x. Of course, it is not the obstruction space because there is no canonical one. And again, here I'm cheating a bit because more or less I'm assuming that X is Gorenstein, because otherwise, if you want to consider only Q Gorenstein deformations, you should consider here the canonical stack, but I don't want to go into this kind of details. And Okay, so basically, when you restrict your moduli stack to these fat points, you have the usual infinitesimal deformation theory, and this gives the local structure of this stack. Okay. So now I just want to briefly say a few properties of deformations of Fano varieties. So the first one is the following. So if X is a smooth Fano variety, then its deformations are unobstructed. Maybe I will write it. So deformations of X are unobstructed. So this is equivalent to say that the deformation functor of X is smooth. And this is a very immediate consequence of Kodaira-Nakano vanishing. Okay, and the proof goes as follows. You take n to be the dimension of X, and then it is clear that there is this isomorphism, because the tangent is the dual of the one forms, the Keller differentials. So there is this equivalence here, this isomorphism. And now, if I want to compute T2x, so I said that T2x is equal to x2 omega x OX. But now both omega x and OX are locally free because I'm assuming that X is smooth. And so when you have an extension, you can dualize and change in the order. So this is the same as x2 of OX omega, tangent. Because X is locally free. So, and now this group is exactly H2 of the tangent. But now H2 of the tangent is equal to H2 of this guy here. So n-1 forms twisted by the anticanonical, and then this 0 here follows from Kodaira-Nakano vanishing. So just to repeat, if X is a smooth Fano variety, then its deformations are unobstructed. So this gives a smooth point in moduli. And this happens also for X, which is mildly singular. So for instance, in dimension 2, if X is a surface and has cyclic quotient singularities, then the deformations are unobstructed. Again, here I'm assuming only Q-Gaussian deformations, otherwise this is not true. And also in dimension 3, if X has terminal singularities, then the deformations of X are unobstructed. And this is a result of Namikawa, and then in the Gorenstein case, and then generalized by Sano in arbitrary case. Okay, so these three examples say that deformations of mildly singular Fano varieties are unobstructed. So if you pick a Fano variety with very mild singularities, then you get a smooth point in the moduli. But there are examples of non-smooth points. So for instance, there exist obstructed Fano threefolds with Gorenstein canonical singularities, and these are produced in the following way. So you fix D, which is a number 8, 7, or 6. And now you consider DPD. So this is the Delpezzo surface of degree D. So of course, when D is equal to 8, there are two Delpezzo surfaces. One is P1 cross P1, and the other one is F1. The first is a good surface, and I mean that DP8 for me is F1. Okay. And a Delpezzo surface of degree D, when D is in this range, is unique and embeds in PD anticanonically. So this is the anticanonical map. Okay. And now you take the projective cone over this embedding, and this gives a threefold, which is singular at the vertex of this cone. And this is a Fano threefold with an isolated Gorenstein canonical singularity. And this threefold is obstructed. And now I want to give the two examples for d equals 6 and d equals 8. Okay, so for d equals 6, so this is the pezzo surface of degree 6. This is the blow up of P2 in 3 points, and this embeds in P6. And if you take the cone over that, then the universal deformation space, I mean, the base of the universal deformation space is this one. So basically, this is, I mean, a local Neterian ring of embedded in dimension 3, and it has two irreducible components. So it has a plane together with a line. So the plane is, I think, the T2, T3 plane, and then T1 is the coordinate on the line. And so basically there are two irreducible components on the universal deformation space. And this means that this singularity can be deformed in two ways. And I should say that this holds both for the singularity, so the vertex of the cone, but this exactly the same works also for the Fano threefold. So it's a global case. And now I want to consider the d equal 8 case. So now I consider dp8 inside, okay, so this is dp8 inside p8. Now you take the cone over this, you can take the affine cone to consider the singularity, or the projective cone to consider the Fano threefold, but the result again is the same. And in this case, the universal deformation space as the base of that is equal to ct over t squared. So this is a fat point. So if you want, this is a singularity which is rigid, it doesn't have any smoothings, but is not infinitesimally rigid. Okay, and try to remember these two examples. Okay. Now I changed the topic a bit, and I want to talk briefly about something which helps me to state a theorem later. And so now let's assume that M, curly M, is an algebraic stack of finite type over C. When I say algebraic, I mean Artin stack. And then Alter created this definition, which is the following. So a good moduli space for M, curly M, is a morphism from curly M to straight M, such that straight M is an algebraic space. So it's not a stack anymore. And then for people that don't know what an algebraic space is, you can think that is a scheme. And then the push forward along phi from quasi-coherent sheaves on curly M to quasi-coherent sheaves on M is exact. And then the functions on the space is equal to the push forward from the functions on the stack. And this is a generalization of coarse moduli space for the Lie-Mumford stacks. So maybe some people are more familiar with this. So if you have a stack which is the Lie-Mumford, this means that the stabilizers are finite. Then there is a theorem due to Kiel and Mori, which says that this stack has a coarse moduli space. And this definition is more or less a generalization of the property of coarse moduli spaces, but now applied to Artin stacks, not to the Lie-Mumford. And an example is given as follows. So here you take a C algebra of finite type, and then with an action of the reductive group G. And now you can create this stack theoretic quotient. And then here you take spectrum of the ring of invariants. And this morphism is a good moduli space. The analogous of this situation in the Delignman first stack case is when G is a finite group. Okay, and this example is basically the local structure of every good moduli space. And this is a very deeper theorem due to Alper, Hall, and Reed. So this example is the local structure of every good moduli space, and this is the Luna et al. Slice theorem. Okay, so sorry if this is a bit too technical, but maybe the idea that you should have in mind is if you have an Artin algebraic stack, which is pretty complicated, and then sometimes there is an algebraic space, maybe a scheme, which approximates the stack. And this space has more or less the same properties of a coarse moduli space for a Delignman first stack. And then people studied what are the conditions on a stack in order to have a good moduli space. But I don't want to talk about this now. Okay. Any questions so far? Okay. So if not, I briefly say something about K-moduli. And so basically, motivated by differential geometry and the existence of Kähler-Ranstam matrix, Tian, Donaldson, and then later many other people introduced in algebraic geometry the notion of K-semistable, K-polystable, and K-stable KLT Fano variety. And I will not say the definition of this, but I think you should consider that these are some Fano varieties. And recently, by following the work of many people, it has been discovered that these special Fano varieties behave well in families, and so you are able to construct sensible moduli stacks and spaces. Indeed, you can construct M, K, SS, and V. So this is KSS stands for K semistable. And this is a substack of the stack of all Fano varieties, where basically now we consider families only families such that the fibers are KLT and K semistable. And then basically several combinations of authors among these people proved the following important theorem: that this is an algebraic stack of finite type over C. It admits a good moduli space, which I denote in this way, M, K, P, S, and V. This is a separated algebraic space of finite type over C. And the closed points of this algebraic space is the set of K polystable Fano varieties of dimension n and anti-canonical volume V. So basically, using the theory of good moduli spaces from the previous slide applied to this stack, you are able to construct an algebraic space, hopefully a scheme, it is not clear yet, which is separated. And so basically all the problems of the non-separatedness of moduli of Fano disappear. Okay. And the other thing that I should say is that basically in the proof of this, it is also proved that this embedding here is open. So somehow being K semistable is an open condition on a family of Fano varieties. And so the fact that this is open means that when you consider the local properties of this stack, the K-moduli stack, yeah, maybe I should say that this is called K-moduli stack. and this is called K-moduli space. So the fact that the K-moduli stack inside the stack of Fano is open, this means that the local properties are the same. And then you can apply the usual infinitesimal deformation theory that I briefly sketched before. Okay, and then of course there are obvious questions. For instance, what are the geometric properties of this stack and space if these stacks are smooth, for instance? Because as I told you, if a Fano variety is mildly singular, then it gives a smooth point in moduli. But then I also gave you these examples of cones over their Peso surfaces, and these are have obstructed deformation, so they are not smooth. They don't give smooth points in moduli, but maybe these points don't appear on these stacks. And indeed, the examples that I gave you don't appear because they are not K-polystable. Another situation is, for instance, the case of cubic trifolds, and this also cubic fourfolds recently by Liu, where basically case stability for this kind of Fano varieties has been analyzed, and this is equivalent to the GIT stability. So basically, this proves that the K-moduli stack is the stack theoretic quotient of the linear system of cubic trifolds modulo PGL5, so the automorphism group of P4. And so this is a smooth stack. And then if you have a global quotient, this is a reductive group, you can create the GIT quotient, which is the good moduli space. And basically the goal of this talk is to produce, using toric geometry, some examples where this K-moduli stack and K-moduli space are not smooth. In particular, I will show you an example where this stack and space are not unibranch. So this means that locally there are different irreducible components, but I can work only étale locally. And another example where it is not reduced. Okay, any questions before I go to the examples?
So, so the difference with surfaces, for instance, if you take, okay, I don't know about cubic trifolds, but if you take cubic surfaces, the moduli space is certainly not smooth.
Huh, I didn't know that.
I think because it's the weighted projective space, right? So that has singularities.
Yeah, but it has a finite quotient singularities.
Yeah. So I guess my question is, the moduli stack is smooth in that case?
Yes, but in general, if you have a smooth Deliman-4 stack, the coarse moduli space is a normal variety with finite quotient singularities.
Ah, okay.
So it's the smoothness of the stack. I was a bit sloppy, but the smoothness of the stack is more or less equivalent to the fact that the space has finite quotient singularities.
Okay, so the interest of this is that we have basically there's no unibranch, or that is not reduced, right? That's the
you're right.
Yeah, okay. Thanks.
Yes. Yeah, so it's definitely unibranch, your example, yes. Okay, so the example is done by using toric geometry, and now I constructed these two polytopes. So how should I think of these two polytopes? So the first thing is that you should consider, let's start from P, so the polytope on the right. And now you constructed this hexagon. So this is a lattice polygon. And now you should imagine that you put this hexagon at height 1. So basically this hexagon on the top here this is height. Actually, let's call it Z equal 1, and then the hexagon at the bottom is on the plane Z equal -1, and then here there is the origin. So this point in the middle is the origin. Okay. So for instance, this point here is the point -1, 0, 1. Let's make another example. This point here is the point 0, -1, -1. Okay, so this is how we constructed this prism P. Okay, and this P lives in a lattice. Let's call it N, which is Z to the 3. Okay, now we can consider M the dual lattice. And again, this is isomorphic to Z to the 3. Okay. And if I denote by, I don't know, Langle and Rango, the duality pairing between them. And actually, I also consider the extensions to the reals. So actually this one. Basically, Q is the polar of P. So in other words, Q is equal to X in MR, such that for every Y in P, XY is at least -1. Okay. And so basically Q and P are mutually dual to each other. And so you can see, for instance, that there is a one-to-one correspondence between facets of P and vertices of Q, vertices of P and facets of Q, and edges of P and edges of Q. So for instance, the top point of Q, corresponds to the bottom face of P. And yeah, that is how you construct the the polar polytope. Okay, and now I consider sigma the face fan of P. So this is the collection of cones such that they are cones with apex at the origin, and they are spanned by the vertices of the facets. So the vertices become the rays. Or equivalently, sigma is the normal fan of Q. Okay, and now I could consider X to be the toric variety associated to sigma. This is a toric fan variety. And if you prepare the description of sigma in terms of the normal fan of Q, then it is clear that Q is the moment polytope of the anti-canonical polarization of X. If you are more familiar with, let's say, the symplectic geometry side of things. Okay, so this X is our example. Okay, so basically X is a toric Fano threefold. This is quite obvious. And it has Gorenstein canonical singularities. This again follows from the fact that P and Q are dual to each other. The K polystability, so X is also K polystable, and this follows from the fact that the barycenter of Q is the origin. And here we are using a result due to Bell, I suppose. And then one can compute the degree of this variety, and this is 12. This is because in toric geometry, all the invariants can be computed combinatorially, and this is the volume of the polytope Q. Okay. The second statement of our result is that the base of the universal deformation space of X is given by this local Neterian ring. So this is this has embedding dimension 24, and there are 4 equations, which are T1, T2, T1, T3, T4, T5, and T4, T6. So this space has 4 irreducible components. So there is the component of dimension 22, which is given by the equation T1 equal T4 equals 0. Then there are 2 components. So this has dimension 22. There are 2 components of dimension 21, and then there is a 4th component of dimension 20. And we prove that X deforms to 3 different smooth Fano trifolds along these different components. So for instance, on the 22-dimensional component, X deforms to Mori Mukai to 6, and by this I mean the 6th entry in the list of Mori Mukai of Fano trifolds of Picard rank 2. So this row denotes the Picard rank. And also in the last column, I also wrote down H12. This is a Hodge number. Then on the 21-dimensional component, X deforms to V12, which is a smooth Fano threefold of Picard rank 1. And then on the 20-dimensional component, it deforms to a Fano threefold of Picard rank 3. And now I want to briefly sketch how we can prove this theorem. So the first part, so actually the first bullet point is basically trivial, following the work of other people. The second bullet point is infinitesimal deformation theory, and of course using a bit about toric varieties. And then the third bullet point is more topological, because once we know what are the smoothings, we have to understand what are the Betti numbers in order to identify to which smooth Fano threefolds X deforms to. And this is a computation done with vanishing cycles. So basically more topology. Okay, so the ingredients of the proof. So the first ingredient is the following. Remember that P is a hexagonal prism. So P is the hexagonal prism. So it is given by this guy here. And then basically the top face and the bottom face are the 2 hexagons. And they give 2 isolated singularities on X, which I denote Q1 and Q2. And these singularities are exactly the singularities studied by Klaus Halfman. So these are the vertex of the affine cone over the anti-canonical embedding of the Delpezzo surface of degree 6 inside P6. And so in particular, if I consider the deformation of the germ of these singularities, this is, as I said before, this is C, T1, T2, T3, modulo T1, T2, T1, T3. So this is this guy here, the union of a plane with a line. Okay. These are not the unique singularities of X. There is also another component, maybe write with a different color. So the singularity of X is Q1, Q2. These are 2 isolated points. And then there is a curve, which I denote by gamma, which has 6 irreducible components. And this corresponds to the 6 edges of the prism, the vertical ones. And one should compute this space, T1x, which is the tangent space of the deformation functor. And using the fact that X is Fano, this is the same as H0 of the T1 sheaf. And one can compute the T1 sheaf, basically, and to try to understand what is this guy. And using this computation, it is very easy to prove that this forgetful map is smooth of relative dimension 18. What is this guy, this map? So here you have deformations of X. Here I take deformations of the germ around the singular point Q1, and here deformations of the germ, the singular point Q2. And of course, if you have a global deformation of X, then if you take the restriction, this gives a deformation of the germ of the singular point. And of course, you can create this forgetful map, and using some ordinary machinery in deformation theory, this map is smooth of relative dimension 18. And this basically gives the proof of the fact that the universal deformation space of X has that base, because this proves that def X, here maybe too sloppy, but is equivalent to C to the 18 times this germ and this germ. Maybe let's call it T4, T5, and T6. And this is the proof of the universal deformation. And then, as I said before, now you should understand what are the vanishing cycles on these 4 smoothings of X. And this allows you to understand what are the Betti numbers of the smoothings, and then basically to locate the smoothings in the list, the tables of smooth Fano triples. Okay. Any questions so far about this example? Okay. So now I want to go back to the stack picture. So now let's call A the base of the universal deformation space, which we have computed. Then we call G the automorphism group of X. And since X is a toric variety with some special properties, you can compute explicitly the automorphism group. And indeed, here there is the big torus of X. And then there is a finite group, which is the automorphism group of the polytope. Remember that P is a hexagonal prism, and this group has order 24, and it is the dihedral group of order 12. So this is the dihedral group of the hexagon. So you can apply every symmetry of the hexagon. And then there is also this cyclic group C2. So C2 for me is mod 2. And this is basically swapping top and bottom. In the polytope P. And this involution is very important, as I will say in a minute. And now we apply the Lunaital slice theorem. Here we have the K-moduli stack of Fano threefolds of degree 12, and here the K-moduli space. And then we have here a Cartesian diagram where here we have the stack theoretic quotient, spec of A modulo G, and then spec A to the G. And since everything is so explicit, so we are able to understand what is the action of G on A, and this allows us to compute what is this ring A, the invariant part of A under G. And we discovered that this has 3 irreducible components. And this is somehow something that we expected, because this involution, swapping top and bottom, basically it identifies 2 components of spec A inside 1 in spec A G. And on this component, so remember that there were 4 components in spec A, and on 2 components, we have a deformation from X to B12. and then this gives exactly one component in the moduli. Okay, and so X gives a non-smooth point in the K-moduli stack and in the K-moduli space, and so we can say that also they are not unibranch. And the same works if you take X, if you take the product of X with the Z space, for instance, and this gives a non-smooth points in every dimension, actually not unibranch points in every dimension. Okay, any question about this example?
So I'm guessing that the period sequence is just where you put 2 or 3 in the middle at the top, and there's 2 different ways of doing that, and yeah, exactly. And then it's just swapping. Yeah, perfect. Cheers.
Yeah, I cheated a bit in the sense that I should have declared my intellectual debt to the Fano search people, in the sense that I discovered this example by exactly using the graded ring database and then all the expertise about period sequences and Laurent polynomials in order to get Fano varieties. Otherwise, I would have never picked this example if I didn't have the more or less the expectations from the Fano search, mirror symmetry conjecture, let's say. Yes. Other things? Okay. Now I want to present the second example, which is the non-reduced one. And now I consider this polytope. This is again, so now I denote this polytope P, and this is in N. This time I don't talk about Q because this polytope is not reflexive. So Q is not a lattice polytope. So the top face of this polytope is this polygon here. This is a polygon with 4 edges, and this is the top face. And now what I do is I consider the symmetry with respect to the origin, and so this becomes this one. And this is the bottom face. And now, and then I take the convex hull of this situation. Again, the top face is on the plane z equal 1, and the bottom face is on the plane z equal -1. And then I consider sigma to be the face fan of P, and then X to be the toric variety associated to sigma. Let's talk briefly about the singularities of X. So the first example, the first couple of singularities is the top face and the bottom face. So this gives 2 isolated points. And remember, this polygon appeared in my previous discussion of the work of Klaus Altmann. So here I get basically the vertex of the cone over F1 inside P8. So the bottom face and the top face give these 2 isolated singularities, which are the vertex of the cone of the first Hilbert surface inside P8. And the universal deformation space of this singularity is, as I said before, CT modulo T square. Then there are, if you consider, there are basically 4 big triangles. Let's denote with green. So there is this big triangle here. Then there is this other big triangle in front. And then there are other 2 on the other side, so, on the back. And this gives basically 4 singularities, which are isolated, but not Gaudenstein. These are terminal singularities. This is 1/3, 1, 1, 2. These singularities are isolated non-terminal, isolated and non-Gorenstein and terminal, but the canonical cover of these singularities is A3, because 3 is co-prime with 4, and where 4 is 1 plus 1 plus 2. And so this means that these singularities are Q-Gorenstein rigid, and they don't give any contribution to the deformations of X. So these are QG rigid. Okay, so basically they don't contribute. And then there is a last situation, which is the following. So you see that basically, if you take this vertical edge and also this one, because of course there is a symmetry, there is an interior point, an interior lattice point in this edge, and this gives a singularity along the curve. So basically here there are two curves, let's call it C, where X has transverse A1 singularity along C. And of course, C is isomorphic to P1. And then one can compute what is the T1 sheaf along this curve. And the computation says that T1X in a neighborhood of C is isomorphic to OC minus 2. Because of course it is a line bundle on the singular locus. And so this means that when you take H0 of this sheaf, this vanishes. So they doesn't not contribute. So they don't contribute to T1X. And so basically the answer of what is a T1X is given only by these two quadrilateral facets. So I hope it should be written in the next slide. Yes. So X is K polystable. So this follows from the fact that P, the barycenter of the polar of P is the origin, and this is obvious because P is centrally symmetric. So this is a Fano threefold with canonical singularities. I didn't write Gorenstein because it's not Gorenstein. The anti-canonical degree is 44/3. And then the mini-vector deformation space is this guy. So this is exactly, basically, the product of the deformations of these two special singular points, the bottom face and the top face. So if I denote A to this base of the mini-vector deformation space, then I consider G the automorphism group of X. And again, in this case, we can compute it because this is the torus. And then we have the automorphism group of the polytope P. This is the non-cyclic group over the 4. So basically there are two involutions, and one involution is the symmetry with respect to the origin, and the other involution is swapping the front of the polytope with the back. So it's kind of a reflection through the plane containing these two red edges. Okay, and then we can compute explicitly the action of this group on A, and then we find that the invariant part of this ring, AG, is exactly CT over T squared. And then again, we use the Lunaital slice theorem, which produces this Cartesian diagram where the stack theoretic quotient of spec of A modulo G is the infinitesimal structure of the stack, and the spec of the invariant part, the invariant subring, is the local structure of the K-moduli space. And an obvious corollary is the fact that there exists a connected component in this K-moduli space, which is isomorphic to the spectrum of this ring, which is CT over T squared. So this is a fact point. And this is basically the end of my talk. And I thank you for your attention.